Hello everyone, my name is Annika Smith and welcome to my 10th and last video of the Stat 231 series, at least before the final exam tomorrow. Maybe I'll make some more in the future to help myself out before I have to take Stat 371, 372, but in the meantime I have other finals to worry about, so no more videos from me. But to conclude this series for now, I have this question, and it's from Chapter 7. It's based on the multinomial model. So we're just testing if the multinomial model with like the same theta is appropriate for this kind of situation here. I'm not quite sure if I worded this in the way that you would expect to see it on the final or anything, but I would suggest you look at chapter 7, problem number 1 from the course notes because it's very, very similar to this example here, and it can kind of like you can see the language that's used for these like kind of questions. And then after I'm done this question, I'll just go over a few notes because I won't be able to cover the rest of chapter 7, but I want to point out some of the other things we do in chapter 7, just so you have a general idea and you can go try it yourself. So, to get into this question, I'm curious as to how many of my fellow classmates are procrastinators, and I asked 600 of the people in our section, what is the biggest distraction in your most recent study session? And the data is summarized here. This is all made up, of course. I did not survey. 55 was enough for me in video 7. I did not need to go and do a whole 600. So, um, we were asked to test the hypothesis that each of the options are equally likely to be chosen by a random student. So now, if you're kind of familiar with Chapter 7 by this point, as I sincerely hope you are, I would, well, you might be thinking, okay, well, are we using the likelihood ratio test or the Pearson goodness of fit test? And the short answer is I'm using both of them for this video just to show you them. I expect on the final we would be either told to do one or just you can do either of them and see how it goes. Um, but I'll be demonstrating both here just for the sake of doing that. So, to get started with this, first we have to write out our null hypothesis. And what is that going to be? Well, it's going to be that theta is equal to, like, the probability of each of these is the same. So how many categories are there? There's 1, 2, 3, 4, 5, 6, 7, 8 categories. So our probability is theta is equal to 1 over 8, and this is a vector of thetas for each of these different types of distractions. And then our alternative hypothesis over here is that, oh, at least 1 theta does not equal 1 over 8. So now I'm just going to take a step back here. You don't necessarily need to do this, but I think it's good practice and good intuition. Think about if this makes sense. So say we have 600 people, and if we're saying that the probability of someone just picking one of these things is random and evenly distributed, then we'd expect to see around the same number in each category. But look, all these numbers are kind of high, except for existential dread here is 10. So that's a lot lower than the rest of them. So I might be thinking, okay, maybe the rest of them have the same probability, but this existential dread thing does not look like it's very common. So, and I mean, if that's one of you, don't worry about it. You're still valid, but it might not be super common. Or maybe it is super common, I have no idea. But in this example here, I'm thinking, okay, because of that category being really small, I'm probably going to get a small p-value, which is going to tell me that my null hypothesis is, like, I have more evidence against it, and then I'd be leaning towards this alternative hypothesis. So that's just my intuition there, but we have to actually go ahead and calculate these using the likelihood ratio test and the Pearson goodness of fit test. So let's get into that. So here's my cheat sheet. I know it looks really messy, but I'll walk you through it. So this value here, this is basically like our little d or little lambda, whatever you want to call it, that we're using. It's the thing that we like shove into the p of chi squared thing. And the way we calculate it is we do 2 times this sum from I equals 1 to k of yi times ln of yi over ei. And once we calculate this whole thing, we just shove it into our chi squared with k minus 1 minus p degrees of freedom. And then that's it. It sounds like a lot and it looks like a lot, but trust me, after you do a couple examples, it's like one of the probably, well, yeah, it's like not that bad. Just trust me. So, as we go through, the most annoying part is the calculation, by the way, which we're about to do. But I'm going to calculate my test statistic here, and it's going to be equal to 2 times the sum from j equals 1, doesn't really matter what index I use, to k of yj ln of yj over ej. Okay, well, let's think about what EJ is. So there's different scenarios. Say if we're trying to test the Poisson model, you would have to calculate EJ using the PDF of, or no, PMF of the Poisson. Or say if you were doing the binomial, you'd have to use the PMF of the binomial, all that. But luckily, because we're in this multinomial scenario with all the thetas being equal, our EJ is literally just n over k, which I have written over here. EJ equals n over k for the multinomial. So let's just stick this up here. And what is n and what is k? Well, n is just our total number of people who we have. And then k is our number of categories. So we count again, 1, 2, 3, 4, 5, 6, 7, 8. And this is equal to 75. Plug it in your calculator. So that's our EJ, and it's going to be the same for all of these. In other cases, if you're trying to test the Poisson or the binomial or whatever it is you're doing, you're probably going to have different EJs. And then this notion of like collapsing categories when EJ is less than 5 also comes in. But because we're doing the multinomial model here, that does not apply. So we don't have to worry about collapsing categories or anything. We can just run with what we have. So this guy here is going to be equal to 2 times yj, and all the yj's are just these guys here that we're given. So my first yj is 85 times ln of the yj over ej, which we said was 75. And then it's just a lot of writing from here. 91 times ln of 91 over 75 plus 70 ln of 70 over 75. And you just painstakingly go through this, and you're going to have to plug this all in your calculator on the final. I know I will be checking that calculation like at least 3 times, because I feel like that's very easy marks for me to just miss out on, just not plugging this in my calculator correctly. But we were told we have to do it, so alas, here we are. But yeah, write everything out, get those part marks if you can't quite make it into your calculator correctly. So I write out my whole thing here. And then I can calculate this. Luckily, I have R to help me with this, so I'm just going to do that. Where is my R here? Oh. Okay, so 608, we see that's 75. Great. We got lambda, and it's this whole thing here, and we see it's 133, which is a ridiculously large value. Like, as soon as I see something like that, I should be like, whoa, like this p-value is going to be so ridiculously small that, like, I don't, like, it's basically, I feel like it's guaranteed. It's not guaranteed. Nothing's really guaranteed in statistics, but it's like, it's pretty small. So, what we go, like, I'd say if it's like, I feel like most of the examples I've seen, if it's like above 10 or 20, like it's going to be a pretty significant p-value. Anything other than that, I don't know, just play around with it a little bit, build some intuition. It's good to like see as you're going through the steps what we should expect to have as our final answer, and it helps you check over your work anyways. So we got our 133.8 or whatever it was. I don't even really need to care about so many decimal places because I know this is ridiculously large. But now I have to do my next step, which is to plug this into the chi-square distribution. So let's talk about this. Well, we're given this part here. Now, this is kind of misleading because for the multinomial model, I literally don't know how to explain this to you. All I can do is hold you by the shoulders and tell you, trust me, bro, it is just k minus 1. The p does not exist. I don't know why, but that's just how it is. So, with other distributions, the p is, as James put it in his slides, p represents the number of parameters estimated in the null hypothesis. But for whatever reason, I can't describe it. Asks on Piazza, I don't know. For doing multinomial stuff like this, it's just going to be k minus 1. The p is 0. So with that said, just take my word for it. The degrees of freedom is going to be k minus 1, which is equal to 8 minus 1, which is 7. So once we plug that into the p of chi-squared function, we would have that we put our 133 in like this, and then we have degrees of freedom is equal to 7, and we need to make sure we put in that lower tail equals false, or we do the 1 minus the thing, whatever floats your boat, whatever we get. Lower dot tail equals false, and then this will give me my p-value, which I have in R again, So we can do that. Just make sure I run these guys. And as I expected, this is a ridiculously small p-value, 1.968 to the negative 26. So, or times 10 to the negative 26. So, whatever it was, blah, blah, times 10 to the negative 26. So I don't even need to look at my chart. I've worked enough with my little chart to know what this is going to be, but I'll just look at it for the sake of it. So clearly, we fall into this category here. And this indicates that there is very strong evidence against H naught based on the observed data. So I can jump back over here. Therefore, there is very, oh, this pen isn't really not working, strong evidence against H naught based on the observed, oh, pretend you can read that, data. So that's using the likelihood ratio test, and you do a very similar thing for, say, if you're testing for the Poisson or the binomial. It's just you'd have to calculate your expected frequencies differently, and you'd have to collapse those expected frequencies if they are less than 5. So I would recommend looking at Caitlin's video example for that. It's posted on Learn under like the final exam folder, and she does a great job of explaining that. That's how I learned how to do it, honestly. So I recommend going there. But with that, I have another copy of this just so we can retry the question using the Pearson goodness of fit test statistic. And it's basically the exact same. It's just a different formula that we use. So what is that formula? Well, we can just write out our null hypothesis again. That's theta is equal to 1 over 8. Our alternative is that at least 1 theta, oh, okay, is not 1 over 8. Sure. And then we want to calculate our Pearson goodness of fit test statistic, which is this guy here. So I still have my yi's, I still have my ei's, the exact same thing. It's just a different formula to compute this. So we do little d is equal to the sum of j equals 1 to k of yj minus ej squared over ej. And remember that ej was 75 that we computed earlier. And we get that this guy, 85 minus 75 squared over, oh gosh, here we go, 85 plus, I don't know if I want to make you guys sit through all this again. So, this is a 75 here, if that was confusing. I'll just do a couple more just to demonstrate this. 70 minus 75. I'm just getting these numbers from the data that I'm giving up here, just like the last example. And let's just do the last one. Oh, because my pen is gonna like crash out on me. So we get this whole thing here. Do all 8 terms, plug it in your calculator, like snuffle back your tears or whatever, and we put that all in here. And you get that D is 100.746. And this is, again, ridiculously large. So we're expecting a very small p-value. So whatever it was, like 100, sure. And when we do our p-value, we get that, again, we have the exact same calculation here, the k minus 1 minus p, but I'm going to hold you by the shoulders. Trust me, bro, it's just k minus 1 for the multinomial. I don't know why. So, we have that it's the exact same as before, our 7 degrees of freedom. Hold on. Did I do 7? Oh, I see that this is a typo because I thought all my life that it was 6 degrees of freedom. It's not, it's 7. Let's see what this looks like now. Okay. Oh, wait, let's just okay, it's still really small. Doesn't change my answer. That's also really small, but I'll get to that. So, 7 degrees of freedom. Trust me, bro. And I hope I put that up here too. Yeah, okay. And then, so I calculate this, I got like 100 or whatever, and then p of chi squared of d, which was 100 degrees of freedom 7, lower tail equals false, calculate that again, and we get this ridiculously small number again. So times 10 to the negative 19. I don't even need to look at my thing. I've actually memorized this sentence already, so there is strong. Oh, wait, nope, very strong. Did I write the right thing up here? Yeah, okay. So maybe I should check the chart every time. Good thing we are given it. Very strong evidence. Okay. There's very. Why is my pen not working anymore? Oh, brother. Okay. Technical difficulties, but I do not want to refilm this, so I want to see if I can salvage this. Maybe if I like refresh this tab, it'll like work. Because it's like getting late and I really want to get this video to you guys, but I'm like too late. Oh no, spoiler alert. Okay, let's zoom in here. Nope, too much. Okay, we are salvaging this. Okay, not retaking it this time. Oh, sure. Okay, there is very strong evidence against H naught based on the observed data. I know this point was very overemphasized on midterm 2, so make sure you don't forget that. And then with that, that concludes my example here. I have some other notes just so to cover all our bases here. Please go and check out Caitlin's Chapter 7 examples in the review video on Learn. I found those incredibly helpful. Went from like, okay, well, maybe I wasn't paying attention to class too much, so that's on me, but I basically learned all of Chapter 7 because of the final review session, and I thank Caitlin profusely for that, so I highly recommend you go and watch those videos as well. And there's also a couple Piazza posts about it, so I'd recommend checking those out as well. There might be some like discrepancies or typos, so if you're not getting the same answers of Caitlin, don't worry, just check Piazza. And then also, when you're doing other goodness of fit tests, make sure you collapse those categories when your EJ is less than 5. Again, one of Caitlin's examples shows that. I did not do that in this because my example just didn't work out that way. And also, please, please, please try contingency table example. I want to bet on my life that there's going to be one on the final. I have no idea if that's actually true or not, but it just like I feel it in my bones. It's going to be there, guys. And again, just look at all the Piazza posts related to Caitlin's videos and Chapter 7 and whatnot. Just keep up with that. And with that, I thank you all so much for joining me on this journey. I wish you the best of luck on the final exam. And yeah, thank you for all your support. Here's a cute picture of a capybara for you. Love these guys. And I look forward to seeing you in a future course.